Hello, hello. Welcome back, guys. We're into, it's so strange, but the final podcast of this week, just the way that things have been split up here. Now, percentage yield is the one that we're going into, which relates quite a bit, in fact, completely into actual laboratory type evidence. Now, honestly, in relation to percentage yield, in relation to solution stoichiometry, we would have been doing a few labs in class. So I'm going to somewhat mimic one here in this last step here with the lab investigation to show you the type of lab we could have done to give you a bit of a taste of the technique and some of the calculations that would be based on it. So that's why there's fewer podcasts, because there's that lab investigation instead. But on to percent yield first. There'll be questions associated with this, and it's a skill set you'll need for the lab investigation as well. Now, ultimately, what we're getting into is, again, a few different terms that are really, really important for you to know. First thing first is we're comparing something called predicted yield with something called experimental yield. These are two different things, guys. Predicted is what you expect to happen. So based upon what you're reacting, what amounts you start with, what would you predict the product would be? Versus experimental yield is like, hey, let's do the experiment. Let's see what actually happens. What do we get? And inevitably, they're different amounts, okay? Now, process-wise for this to happen, it is a stoichiometric process. So nothing new there. We have to build again on our past skill sets in order to do this properly, alrighty? Now, the quantity that we expect to get, what we imagine should happen based upon the stoichiometric ratios. Again, this is really important that you have these straight in your head, guys. That's called the predicted value. And there's another word for it, theoretical. They mean the exact same thing, so be prepared for either wording. And theoretically means in theory we should get. In theory, this is what should happen. In theory, this is what we predict. It is not reality. It is the ideal situation. Now, vice versa, the experimental yield is what you actually end up with, right? An actual amount. What happens in the real world, in your experience. So this is what we actually obtain from the reaction. Inevitably, guys, this is a lower amount. Why? Well, there's a variety of different things that impact why this amount is lower. Sometimes you end up with impurities put in there. Sometimes it's poor lab technique, in all honesty. Sometimes you end up with a small amount of the precipitate you're collecting still being a little bit dissolved. Not a lot, but a tiny bit, right? So there's always some slight discrepancy between actual amount and experimental yield, actual amount of predicted yield. Inevitably, if the lab technique is worse or if it's a harder substance to actually collect, there's more of a differential between these two, and your percent error is, well, worse. So guys, just a quick little picture to show you here. This is sort of the technique that could be done when doing this. Now, ultimately, what we have is in this mixture, there would have been two things that reacted together, right? And we put the reaction together and a precipitate would have formed. And the precipitate is what we're trying to get in this filter paper. So they pour down a glass rod just so it doesn't splash up, and so you make sure that it goes where it's supposed to. Now, the residue, which is this, is the precipitate, and that's being collected in the funnel, right? The filtrate is what continues to drip through, and it has any of the aqueous ions still in it. So keep that kind of in the back of your head for when you get into watching the lab investigation later. Okay, new formula. Yay! This is on your formula sheet. So I want you to have a look on, oops, that's not your data sheet, on here. And guys, we are way down here, percent yield, this one. This is what we're using. I want you to look at this. This is dun, 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 the last formula that we will use on this sheet. Percent error is related. We're not going to focus on it here, but percent yield, last one. Whoa! And then officially, we have done all the formulas that we're going to do this year. Yay! Okay. So moving on then, here it is. It's a fairly logical one. Percent yield has the experimental yield, which if you recall back, I said is going to be your lower number. right? Almost always, okay? And for all your questions, it will be. For predicted yield, that's always going to be the higher number. So that kind of helps you to know what goes where. That's probably the biggest error is people are like, ooh, which one do I put on the top? Which one do I put on the bottom? Well, when in doubt, put the lower number on the top and the higher number on the bottom, okay? You're not going to get more than 100% yield in these questions. Alrighty, let's look at a really simplistic type question involving this formula, just so you get used to it. If we heat magnesium metal in air, it'll react with the oxygen there. What do you get as a result? Magnesium oxide. So it says, hey, we're going to react 2.5 grams of magnesium. Cool. Then when we do that, the predicted yield, which we would get from stoichiometry, is 4.15 grams. So this is in theory what we would get. Vice versa, the actual mass of product was only 3.96. Now here's where it comes into which one goes on the top. Well, between 4.15 grams and 3.96 grams, 3.96 is the smaller number. It goes on the top, guys. Pretty much always the smaller number will be the experimental yield. So step by step, and I expect to see this in your work, write down, of course, the formula first. Percent yield is equal to the experimental yield. Uh-oh, my pen's going wonky. Experimental yield divided by our predicted yield. And of course, times by that 100%. Okay, so I'm going to put the lower number on the top, which is what we actually got, the experimental amount, 3.96 grams, divided by what my predicted yield was, what I thought I would get, oh, sorry guys, I don't know what my pen's doing here. 4.15, oh boy, let's try again. 4.15 grams, there we've got it, times that 100%. Okay, let me redo these numbers a bit here. Make this look a little bit better. 3.96, come on, 6 grams. There we go. Number crunch those out, guys. One divided by the other. Sig dig still applies for this. So we have 3 sig digs in the questions, which means my percent yield needs 3 sig digs as well. It's going to be 95. Come on, this silly thing. I think my iPad's getting a little bit hot and bothered. I've been using it for kind of a long time today, so it gets a little bit tired. Let me try if I can write down here if that'll work. We get 95.4%. There we go. 3 sig digs. There's my total yield. No big deal, guys. Okay, when you see it that way, it's like, oh yeah, I got this. Yeah, the questions do get more complicated. Case in point. And this is somewhat similar to experimental data you would get. So this student comes along and they mix 2 solutions. So we have essentially 2 ionic compounds. The first solution is potassium phosphate. Notice that you're given a volume and a concentration of it. The second solution is calcium nitrate. Notice again, you're given a volume and a concentration. Uh-oh, guys, which one runs out first? Well, we don't know. You have the ability to figure out the number of moles of both reactants. In other words, you're going to have to take the time to figure out what is the limiting reagent here. Uh-oh. Okay. Here's the other twist. Massive filter paper. Well, why is there filter paper? Remember that setup I showed you, right? Where I said, hey, this is kind of what it looks like. Well, you'd have the filter paper that you'd have to get the mass of first before you start filtering. Otherwise, we don't know what to subtract, right? So we'd have the mass of the filter paper, and then we have the mass of the paper with the precipitate. Of course, it's a lot higher. Well, we need to take those 2 numbers and subtract them so that we can actually determine what the experimental yield was. 2.85 minus 1.14 grams, we get 1.71 grams. Now, this is not stoichiometric at all. This is the experimental yield. So this is just something that you got to take in your brain and keep in the back of your head that we're going to use this later for the percent error. Right now, just leave it alone, right? At this point, it's not going to be touched till we get to the percent yield. Okay, I'm going to move on to the next page so that I have room to do this, but keep those numbers in the back of your head. And here we go. So first things first, as per usual, we need a balanced chemical reaction. We have potassium phosphate that is reacting. So potassium phosphate K3PO4 aqueous. Why aqueous? Because these are ionic compounds in a double replacement reaction, which means, yeah, we do need to use our aqueous state of matter. Calcium nitrate is the next one, and it is aqueous as well. Double replacement, the cations are going to switch places. We will end up with KNO3. Check the solubility, it is aqueous. And we also end up with calcium Ca3 bracket PO4 2. And when you check the solubility of that one, lo and behold, ding, 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 there is our precipitate, which is important because that's what got dried up in the filter paper, right? When you reacted the two solutions, a precipitate formed, a solid formed, that's what we collected. Okay, let's start to go through this data to figure out what on earth the limiting reagent is here. And the whole purpose of what we're doing right now is to figure out the predicted yield. What do we in theory think we should have had for an amount of precipitate? Then we can compare that to the experimental one that we got here, highlighted in yellow. Okay, here we go. From the given data, the volume of the potassium phosphate divided by 1,000 to put into liters, 0.0850 liters. The concentration of that solution is 0.172 moles per liter. I'm going to take N equals C times V and number crunch those, 0.172 moles per liter times 0.0850 liters. Liters cancel out. The number of moles of potassium phosphate is going to be 0. Here we go. 0.01462 moles. Okay, leave it at that for now. Now we need to figure out how to find the calcium nitrate so we can do a comparison. So once again, we've been given the volume. It's 0.1200 liters. In other words, 120 mils divided by 1,000. Concentration, 0.144 moles per liter. Exact same process. N equals C times V. 0.144 moles per liter times that 0.1200 liters. Liters cancel out. The number of moles of calcium nitrate is equal to 0.01728 moles. Now think back to limiting reagents. I cannot compare those two yet. First thing I need to do is use my balancing. Speaking of which, I didn't balance this yet. So let's go back and balance it. We're going to need to have 2 of the potassium phosphates, 3 of my calcium nitrates, and of course 6 potassium nitrates here. There we go. Okay, so take those and divide by them. If I've got a 2 here, I'm going to have to divide that number by 2. If I've got a 3 here, I'm going to have to divide this amount by 3, right? So divided by 2, divided by 3. Then I'm able to compare how they actually ratio-wise relate to each other. I get 0.00731 moles versus 0.00576 moles. Now it's the simple question of which one's smaller. Well, 0.005 is less than 0.007. Ding, ding, ding. This one won. That is my limiting reagent. The calcium nitrate will run out first. So when I do my stoichiometry, I'm going to ignore the potassium phosphate because it was not in limiting amounts. It's in excess. You won't run out. So I need to use the limiting reagent, the calcium nitrate, to compare. Okay, let's do a mole ratio then. So going over to the next one, we will compare our calcium phosphate to the calcium nitrate. It is a 1 mole to 3 mole ratio. And I'm going to see what amount I have on top. And remember, go back, we need to use this number, right? The 0.0172, because that's the actual amount reacted. So divided by 0.01728 moles. Cross multiply and divide. X is equal to 1 mole times 0.0178 moles divided by 3 moles. Number crunch, X is equal to 0.00576 moles of calcium phosphate. Well, that's all well and good, but I need a mass to compare to because that's what I have for my experimental value, a mass of precipitate. So I'm going to take that and I'm going to get mass equal to N number of moles times the molar mass. So hopefully you've calculated the molar mass before, right? You should write those down, have those 0.00576 moles. And when you number crunch it, the molar mass of that calcium phosphate is 310.18 grams per mole. Number crunch, mass is equal to, I'm not going to round yet, this is now my predicted mass. In theory, this is what I should get, 1.78 ... grams. Whew, lots going on. Now, at first glance, it seems like we're finished, but the whole purpose of the question says, what is the percent yield? So we're not actually finished. We need to get percent yield. How do we do that? Well, we have two things. Percent yield is equal to the experimental yield, which we found by subtracting the final mass from the filter paper mass, divided by the predicted yield, which is what we just spent a whole bunch of time calculating, times 100%. The experimental yield we got before was that 1.71 grams, right? If you think back, I got that from right here, okay? So I take that, divided by what we just got, 1.78 ... grams, times 100%. Oh, almost done. I know these are long, guys, right? Okay, and end result, 95.7%, 3 sig digs. There it is, done and done. And there you have it. Figuring out how percent yield goes into stoichiometry, goes into limiting reagents, excess reagents. It's like our whole course in one question, pretty much. All right, guys, you can now complete 4, 5, and 6 in the weekly assignment. And once you're done that, you are ready to move on to the lab. So please continue with the lab. It's actually not particularly complicated. It really walks you through step by step. It should truly be quite easy marks. So take the time to go through it. The lab to watch, you'll only be watching for just over 5 minutes. So it's not particularly time consuming at all. All right, guys. That's it for me. And if you got questions, as per usual, make sure you ask. Talk to you later. Bye-bye.